Yeah, so welcome everyone to today's edition of the Quantum Spain seminar. So today we're very happy to have Henry Semenenko, who's a quantum optics engineer in Quantinuum. And yeah, for those of you who don't know what Quantinuum is one of the, perhaps one of the more important players in the development of hardware in quantum technologies and quantum computing. Specifically, they're well known for the trapped ion experiment that Henry is gonna tell us about today, I believe. So please, Henry, the floor is yours.
Perfect. Well, thank you so much for the introduction. It's a real pleasure to be here and speak as part of the seminar series. Having previously watched some of the other ones, that it's becoming a really nice seminar series to learn lots of different stuff around quantum technologies. And today I'm going to be speaking around our quantum computing hardware. As Avera mentioned, we're working with trapped ions, so I wanted to delve into a little bit of the background of what that is, and then talk about our work in progress with quantum error correction, and finally ending with what the scaling of these kinds of systems looks like to sort of finish off, and how we can continue to grow and to build larger and larger quantum computing systems. So to start with, I wanted to just sort of highlight the background of where this technology came from. The specific architecture that we are developing is this quantum charge coupled device, or QCCD architecture, that was developed from NIST in the late 90s, and it lends a lot of ideas from the same technology which is in camera sensors, where you have arrays of charges that can be transferred between the different parts of the array. Except in our case, we are going to be using ions, and these will be our qubits. So we'll have an individual ion will be our qubit state. But the qubits are mobile, so they're not fixed in a particular place, so we can rearrange them, we can move them around, and this allows for arbitrary connectivity between any qubits. But what is fixed in this architecture is the operation zones. So this will be our gating operations, our state preparation, measurement operations, and they will be in specific locations. What this allows for is for very low crosstalk between the different zones. Also, there's potential for sort of modularity between these different zones as well. And so the qubits themselves will be moved into specific zones depending on the operation to be performed, and this will be on either single ions, single qubits, or pairs of qubits. And so we're avoiding very long chains of ions, and we're really only using sort of singles or pairs at any one time. And to give you a bit more of an idea of what this looks like in terms of our specific hardware, this is a bit of a high-level view of our H1 generation ion trap system. And so the picture at the top here is looking down on the trap. We're using a surface trap, and this will be separated into different zones, as I was talking about from the architectural point of view, which will have different functions. And then we trap ions above the surface of this trap, and we can move them around on the surface into the different zones. The specific qubits that we're using in this architecture is ytterbium-171, and our qubit state will be sort of the hyperfine state of these ions. And this is how we can determine our zeros and ones. The blue balls are the cooling ion that come along with our qubit ion. This ion is a sympathetic coolant. The idea here is that we can cool the motional modes of our qubit states through a Coulomb interaction, but the barium ions in this case, which is our sympathetic coolant, don't hold any quantum information. They're just sort of there as a resource for us to cool down the ions' motional modes. And the different zones here that we sort of will have in our architecture are the purple zone on the right, which will be ion loading. So this is where we can load our neutral atoms in, ionize them, and then trap them into our architecture, into the processor. The two orange zones at either end, these are where we can store ions. So perhaps there's qubits that aren't being used in a particular round of computation. We can store them away from the gating operations. And then finally, in the center, we have the blue zones, which will be our 5 dedicated gating zones. And this is where we'll be able to do single qubit operations, two qubit operations to actually perform quantum computation on our ions. And then with this architecture, we can rearrange any of these ions into any configuration that we need to perform the computation. one thing that's worth mentioning about the specific gate zones is that, we can frequently calibrate these zones, which allows us to have very high fidelity operations, and allows it to be, all-to-all connectivity between any of the ions. And one final thing, the lasers that are going across are the way that we mediate all of the quantum interactions between our ions. And so depending on the specific operation, we will apply laser beams to do single qubit operations, 2 qubits, cooling, state preparation and measurement, all mediated through laser operations. And so just to give you an idea of what this really physically looks like, on the left of this slide, we have a circuit. And what we'd like to be able to do is implement this onto our architecture. And so as we step through the circuit on the left, we'll see physically on the right what's actually happening with each of our different ions and what's happening to each of the qubits. And so initially we start with the all zero state. And so what we just need to be able to do is to prepare the qubit into a well-defined state. And so these will be performed by laser beams that will initialize our qubits into the 0 state. We then want to perform 2 Hadamard operations, and this will be on the red and green qubits, which are already in our operational zones. And so we can perform these operations in parallel. So our operation zones can be done, operations can be done in parallel. We can perform those 2. But before the next time slice, before the next operation, we need to be able to combine the red and green qubit into a single gating zone. And this will allow us to perform the interactions between those ions. So, we slide this green qubit across and we keep them now in the left-hand gate zone, which now allows us to do our 2 qubit operation, our CNOT operation in this case. And so we can apply lasers on this specific zone just to impact those 2 qubits. And then finally, before this next round of 2 qubit operations, we now need to do a rearrangement of our ions. And so we want to make sure that the red and the blue one are in the same gating operation, the same gating zone. And so we need to swap the red and the green and then combine the red and the blue. And this allows us to then perform our second 2 qubit gate, while leaving the green qubit unaffected by this operation. And finally, we can then perform mid-circuit measurement. So in this particular operation, what we're going to do is only measure the green qubit, while the red and blue qubits will be left unaffected. And so we can perform a laser operation only in this specific zone, which allows us to get a measurement and store this in a classical register. And what this will allow for is 2 things. The first is conditional logic. So we can use the output of this measurement to impact what future operations we perform on our qubits. And secondly, this allows us to reinitialize our qubit, and so that this can then be used later on in our algorithm, later on in our circuit. So this is very useful and sort of something that is very critical when we get towards error correction, where you want to be able to measure your qubit operations partway through the circuit and then be able to correct based on those measurement results. And so the real key sort of differentiating features for the QCCD architecture comparing others is sort of the all-to-all connectivity that we have, the rearrangement of our ions. So instead of requiring lots of logical swaps when you have a nearest neighbor connection only, which would have far many more operations that you need to perform, we can instead just rearrange our ions and perform directly the operation with the qubits as necessary. Also, this qubit measurement and reuse, as I was mentioning previously, being able to do conditional logic and feed forward those classical outputs to impact the future circuit. And we're also enabling, high fidelity gates through sort of independent gating zones and fixed gating zones for frequent calibration. And then finally, one thing which sometimes does come up in circuits is variable angled gates. So, we can have an angle gate which is not fixed to a specific operation, but can be a bit more continuous in a spectrum. Okay, and so these particular systems, I was talking about the H1 system. We also have a H2 commercial system, and these are ones that are currently available, through cloud providers that people can run circuits on. And so on the left-hand side, our H1 architecture, this was the linear architecture that I was showing previously, has 20 fully connected qubits. In this operation, there's 5 parallel gating zones and very high fidelity operations with very, very low crosstalk error. In the H2 architecture, which is the sort of next generation that we launched a year ago, now has 56 qubits. I'll talk a little bit more about that in the next slide, with 4 parallel gating zones, very similar 2-qubit gate fidelities, single qubit gate fidelities, state preparation and measurement, and crosstalk errors as well, which are really allowing us to push the possible quantum computations that we can do at this sort of scale of system. The H2 architecture that I was talking about, that commercial system, recently relaunched, was previously running with 32 qubits. We're now running this with 56 fully connected qubits. And what's really impressive from the hardware side is that we've managed to maintain the fidelity of our 2-qubit gate operations while increasing the number of qubits in the system. And we're also now at the point where we're beyond classical simulability. So to be able to do a full vector simulation of this number of qubits would need far in excess of the number of bits of memory that are available even on the largest supercomputers at the moment. And so we're really pushing the boundaries of these kind of systems into territory that is beyond sort of classical computing. This is highlighted by the demonstrations that we performed with random circuit sampling. And so this is an experiment to sort of show quantum advantage, or really to demonstrate that the quantum systems are beyond the possibility or beyond the capabilities of classical supercomputing simulation. And so what we were able to demonstrate with this was 100 times higher fidelity than the previous demonstrations of random circuit sampling. And so these typically have been performed on superconducting experiments. And so this is really highlighting a couple of key things in the architecture of the very high gate fidelity, but also the all-to-all connectivity allows us to achieve these kind of experiments at potentially lower depths as well, because we're not limited by the connectivity between different qubits in our system. And finally, one thing that's worth highlighting and is sometimes important is that the power consumption that we managed to achieve with this system was 30,000 times less than when the system was when the algorithm was run on the supercomputer. And so it's really showing that speed or accuracy may not also always be the limiting factor here, but the power consumption on these systems can also be much lower as well. And so at Quantinuum, we have a long history of benchmarking the systems to really show the performance that we're able to achieve with these. And so this is, we do a huge range of benchmarkings, both at, all at the component level. So some of the specifications that I gave you earlier on the sort of single qubit gates and 2-qubit gates, state preparation and measurement, that we're constantly benchmarking to ensure that the system is meeting the specifications that we're claiming. And then also at the system level, so there's a number of different benchmarks that we've run, the random circuit sampling that I mentioned previously, and quantum volume is one that we have spent a lot of time working on, which I'll discuss a little bit more in the next slide. And now we're also being able to move to the algorithmic level of benchmarking. So are we actually able to run algorithms on this system and comparing them to what other solutions there may be, whether this is classical simulation or other. But I wanted to highlight really quantum volume as a metric that is trying to encompass the entire stack of the quantum computer. So we're not looking at just individual component level or individual gates. We are trying to really stress test the entire process from state preparation to measurement. And the idea here is that the quantum volume measure is the sort of largest circuit that we can run where the depth is equal to the number of qubits. And typically it's presented as this 2 to the power of the minimum of the depth of the circuit versus the qubit number. And so on the left here, we can see this is the circuit that is being calculated. So this will be for a circuit quantum volume of, well, it's depth 4 with 4 qubits. And so in each time step, what we perform is a random 2-qubit SU4 gate. And then we randomly permute all of the qubits, so rearrange them arbitrarily. And then we repeat this process, in this case, 4 times to get our quantum volume measurement. And so we then compare the experimental outputs with the simulated ideal outcomes. And we rearrange the outcomes of this experiment based on the probability. So they are ordered from least likely to have occurred to most likely to have occurred. And we then look at the experimental outputs and we count the number of what are called heavy outputs. And so these are the outcomes which were measured, which were in the top 50% of most likely to have occurred. And then we tally those ones up and we do many rounds of this experiment. And on the top right, this is what we're showing is the number of circuits that we're running, and we're calculating how many heavy outputs we get. If we're above 2/3 with a 2 or 3 sigma confidence, then we're said to have passed the quantum volume test. And you can really see how this particular system is stressing everything from state preparation to gates to measurement, encompassing a good metric to try and take into account all of these different things. And as I mentioned before, quantum volume is something that we've been benchmarking for a number of years with the intention to increase this 10 times year on year. And so earlier this year we were able to show a quantum volume of 2 to the 20. And so we're managing to consistently hit this trend, but obviously we're getting to the point of very, very large systems. There's only so much further that these small systems are able to sort of grow before the errors in our systems will just become too large. And so at this point, we then need to start thinking about going beyond our physical qubits and towards logical qubits and error correction. And so this is really transitioning from this NISQ era through to fault tolerance in a way that we can start to protect our quantum information, detect errors, correct errors, and really drive larger systems and larger circuit depths. And one thing that's really sort of has been thought, while there have been many demonstrations of very useful circuits that are being run on NISQ devices, to gain a sort of true advantage with these kinds of quantum computers or large quantum computers, logical qubits will just be necessary. But it's important to really understand what it is that people mean by logical qubits, because it is important to just have a definition of the things that a logical qubit should satisfy. And so there's not necessarily one definition of this, but this is one that was presented recently in the paper that I will talk about in a few more slides. But the first criteria is to be able to correct all individual circuit errors. And so if there's an error on any single qubit, we're able to measure that and correct for it. The second criteria is to achieve a large separation between the logical and physical error rates. And so we're not looking to generate logical qubits that are just at the physical error rate. We really need to have logical qubits that are much below our physical error rate. So that certainly as we scale this, that we can push these errors much lower and have, again, higher circuit depths. And the final criteria here is to be able to generate entanglement between at least 2 logical qubits. And so what we want to be able to do is have logical qubits that we can interact with one another we could achieve a very good logical qubit on its own, which is very well protected, but is unable to interact with other logical qubits. And so we wouldn't actually be able to perform operations at a logical level, which is really what we want to be able to do as we move towards a fault-tolerant circuit. And I wanted to, just step back a little bit and give a little bit of an error correction refresher, just to introduce some of the terminology that is used in the notation, certainly that is used in quantum error correction, but base it on, what has been done in classical error correction, which is a little bit more familiar to people and perhaps a little bit easier to understand. And really, the key idea in classical error correction is to be able to encode our data with redundancy, and then to be able to detect and correct bit flip errors, which is the only error that can occur in our classical system. And so one example of this, and sort of the simplest example that one might think of, is to use a repetition code. And so here we're going to, instead of sending a single 0 or a single 1, we will just repeat it 3 times. And then to be able to detect and correct, we're just going to use a majority vote. And so we're going to look at the 3 bits that were received and just say which was the most likely outcome to have been the true outcome. And so at the bottom here, we've just got a run through of what this looks like. So we will want to encode our 0, 1, 1. This just gets expanded out. As we transmit this, the bits in bold will get flipped. But because there was only single bit flips in here, we're able to correct that and then decode back to the correct state that we wanted. So in the quantum error correction case, unfortunately, it's not quite as trivial as being able to just copy data. Because of the no cloning theorem, we're not able to just arbitrarily copy quantum states. So instead, what we have to do is use entanglement to generate correlations between the physical qubits, and this creates what we'll call our logical qubit. We're also not able to, we don't just want to correct bit flip errors, but we also need to correct phase flip errors as well. So this, the space in which we need to protect our qubits from errors is a little bit larger. And then we also need to be able to keep our errors from propagating. And so this is linking back to what I was talking about with logical qubits being able to interact and entangle. We need to move away from physical gates to logical gates. So when we perform operations, we do so in a way that is fault tolerant. And then also needing to make sure that whatever gate set that we do have is a universal one, so we can perform any quantum computation that we want. And finally, on this slide, I just wanted to highlight the notation that's commonly used with error correction codes is this NKD. And so the N at the front is the number of physical qubits that we'll use in encoding our logical qubit. The K is the number of logical qubits that is encoded within a specific block. And then D is the code distance. And so this refers to the number of errors that we're able to correct. And so a larger distance means that we can correct more errors, but typically this requires more physical qubits to be able to do. And so at Quantinuum, we've been working on quantum error correction for a number of years. And so, we've really started to demonstrate some of the fundamental aspects of, quantum error correction and generating logical qubits. From all the way on the left, demonstrating the first demonstrations of real-time error correction, really starting to reach the limits of physical errors compared to logical errors. We've shown what are called sort of more error detection codes, this iceberg code, where we can start to really push the bounds of this NISQ era computation by just being able to detect errors with a very low overhead code. We can then apply these kind of techniques to actual algorithms and, doing at the moment, very simple algorithms in terms of a 1-bit addition, but being able to do this in a fault tolerant way on our systems. And finally, looking at things like magic state distillation and resource state generation. And so these ideas of being able to move towards fault tolerance by injecting particular resource states into our computation. And so the last result, this one on the bottom right, is the one that I'm going to highlight on was a result from a few months ago in collaboration with Microsoft and ourselves. And this was showing that we could create logical qubits that are better than the physical error rate, and also demonstrating repeated error correction as well, which is something that is going to be critical in larger systems. And so I just wanted to give a bit of a highlight of the results, and then I'll go through what the results actually were. And so this is looking at logical qubits now with better than physical error rates. And so the two codes that we will be looking at in this particular paper, or that were studied, is first the Steen code. And so this is quite a well-known code. It's 7 physical qubits to encode 1 logical qubit, and has a distance of 3, meaning that we can correct up to a single error. And it's often drawn in this sort of diagram, which really highlights the sort of distance 1 nature to it. So by measuring each of the different zones of this, the red, green, and blue, you can detect whether there was a single error in any of those, and then back calculate on what the error was. So it's a nice way to sort of highlight how that error correction works. And then the other code that will be studied is this carbon code that was developed by Microsoft. This uses 12 physical qubits, so in our case will be 12 ions, to encode 2 logical qubits. And what this means is we get a distance 4 code, which we're still able to correct single qubit errors. But what it also allows us to do is to detect possibly weight 2 errors, not necessarily correct them, but be able to identify that there was an error. And what we're going to be comparing this to is the physical error rate. So if we were to run the same operations in a physical system without any kind of error correction, what error would we expect? We're then going to do error correction and also introduce error rejection. So this is looking at, as I mentioned in the carbon code, where there are where there are weight 2 errors that we're able to sort of reject. And the idea in this result is to look at benchmarking complete quantum circuits. So we're not looking at individual components here. We're not looking at individual gates in this circuit. We're looking at the full operation. And this experiment, these demonstrations, were performed on our H2 processor, which at the time had 32 qubits with 4 parallel gate zones, and it's 99.8% 2-qubit gate fidelities. And so delving in a little bit to the actual demonstration that was performed, and first looking at this Steen code. So as I mentioned, there's 7 data qubits. So these are the 7 physical qubits that make up our logical qubit. But to perform our operations, what this also requires is ancilla qubits that will be used to do our syndrome extraction to check whether there were errors. And so the circuit on the left here that we're looking at, which is to generate logical entanglement, this uses 20 physical qubits. So there's 20 qubit ions that are in this circuit. And the idea is to generate a logical Bell state. So this is entanglement between 2 logical qubits that are encoded independently with our Steen code. And we start initially just by creating our logical states. And so this is done in a repeat until success up to 3 times. So we can try and prepare our 0 state, do some checks to see if there are any errors. If there are, then we can repeat this process and just try and make sure that we have a 0 state, and we'll do this up to 3 times. In the second step, we'll perform a transversal Hadamard, and followed by a transversal C0. And so what this does is it encodes our logical qubits. And what's nice is in this particular code, we can perform these transversally, so they are error protected. We're not propagating any errors in this by really looking at the physical level. And then we perform a single round of flagged syndrome extraction on each logical qubit individually. And so this will allow us to check whether there are any errors in this circuit. And if there are, then we are able to correct for that. And finally, in this red box, we are going to perform transversal gates to rotate the qubits into our desired measurement basis. And so this one, in this particular code, we can rotate transversally in X, Y, or Z bases, and then we can measure the outputs. From the outcomes of this, we are able to then infer what the syndrome measurements would have been. And so it does allow us to check whether there were any errors still in the circuit. And so the results from this demonstration, when we look only at the physical error, we can see that we would expect about a 0.5% error rate. And so an error here is when we measure our Bell state, and because the Bell state should be exactly correlated, we say that there is an error when that parity doesn't match. And so in this case, 0.5% of the time in the physical error, we detected an error. When we look at error correction, and so this is looking at only information that has come from the blue box. And so what we do is we look at the syndrome measurements and also the measurements that have been performed when generating the logical zero states, and we perform this pre-selection to determine whether we would pre-select a state. And in this case, we can already reduce the error almost 10 times to about 0.05% error rate, showing that this error correction is performing better than the physical case. And then if we then, instead of looking at error correction, we just perform error detection, and so we would just reject the states which had a non-trivial syndrome measurement. We actually increase this as an estimated 500 times, and so this is based on the sort of estimated percentages when you look at sort of the low number of samples that we have and what we would expect the error rate to be. And so we are managing to vastly increase what the error correction is. And it's worth mentioning that the idea of generating resource states is a kind of scalable method towards quantum computation, while the sort of traditional post-selection methods where you look at the entire outcome of the circuit and then select whether you want to accept or reject is not a scalable way. But by doing this pre-selection and generating these resource states to inject into our circuit, we can have what are called sort of resource state factories that we can inject in. And so just, provided that we have enough of these and the error rate is, or the acceptance rate is high enough, then this does become scalable in a way to do, large quantum computation. And then, so moving on to the next code was the carbon code. And so this was developed by Microsoft, which again is 12 physical qubits, 12 ions, encoding 2 logical qubits. And this circuit, when we want to encode this, is 30 qubits or 30 ions in total. The reason that we need 2 code blocks here is because the transversal C0 operation that we perform with this code isn't between qubits in the same block. It's between qubits in individual blocks, so 2 separate blocks. And so here, instead of creating one Bell state, we're creating a pair of logical Bell states with this operation. And so, as I was mentioning about the sort of distance of this code, it actually allows us to operate this in 2 different modes of operation. And so the first is similar to the previous round, where we're going to look at doing error correction. So based on the syndrome measurements that we perform, we will attempt to correct the qubit or attempt to correct the error that had occurred and then continue on. In the second mode of operation, we can do error correction and also error rejection. And so depending on the syndrome outcome, the way that the error correction is performed is that we look at the likely Pauli errors to have occurred, but in certain cases, the syndrome measurement will be ambiguous. And so in the error correction operation, if we do solely error correction, then the correction is performed arbitrarily, and if there are errors which have equal weight or equally likely to have occurred, it's just chosen arbitrarily. Whereas in the error rejection regime, we then reject this and instead just would restart this operation if we were generating a resource state. And so one final thing to mention in this particular code, while it does have a transversal C NOT gates, it doesn't have a sort of fault tolerant Y eigenbasis measurement. So the results here are limited only to the X and Z. And actually the results that I presented previously were also only the X and Z bases. So, there is a fair comparison like for like between the two different codes of the operations that were performed. And it's also, I guess, highlighting that instead of performing a Hadamard operation, so there is a transversal Hadamard operation that could be performed here. In this particular regime, it's more beneficial to directly generate our plus state. So we're able to do, sort of verification along the way as we're generating this plus state that allows us to, detect errors as we're performing the circuit. And so the results that we see from the carbon code, the physical error rate, what we're now considering is doing 2 pairs of Bell stairs, which is why, the physical error rate is slightly higher. But this is about 0.8%. And so if we then just look at doing error correction, and so this is when we're looking at the syndromes and actually correcting the errors that we think have occurred, then the error rate, reduces about almost 5 times. But really the interesting point is when we start to look at both error correction and our rejection and being able to, detect whether errors have occurred, this is, 800 times better than we did have at the physical level. And so we're really able to, push the error rate and suppress that far below what we had at the physical level. And on the bottom left here, it's sort of a nice, demonstration of what we're looking at when what we're considering to be an error. So on each side, we've got our pairs of qubits, both physical and logical. And when we compare the outcomes of those, if they match, then we see that pixel would go white, and if they don't, then we see a dark pixel. And so we're showing the discrepancy between the physical level and then at the logical level. We aren't detecting any errors in this particular case once we've done our error correction and error rejection in this regime. And the final result from this paper is showing that we're able to do repeated fault tolerant error correction. And so instead of looking at just a single round of error correction in the previous slides where we created a state and then performed our operations and did our syndrome extraction, here we're going to do repeated measurements of our extraction to see how the error correction really performs over multiple rounds. And moving beyond sort of the physical or the logical component level and more towards the circuit level. And this demonstration uses the carbon code. And so the carbon code has very high thresholds, but to be able to sort of achieve these thresholds, the requirement is to have fresh ancilla qubits to be able to use. When this demonstration was being run with 32 qubits, there wasn't enough space on the system to be able to have 3 code blocks that you would require. So instead, the syndrome extraction in this demonstration is serialized and is performed with a 1 bit sort of teleportation between the different code blocks. So this is sort of shown in the circuit. And then the repetitions that we're going to do is to perform logical circuit. And so the circuit that we can run fault tolerantly whilst using the carbon code is shown at the bottom, where we can perform our X and Z rotations depending on a chosen rotation value. And then we can also perform these C0 and CZ operations. And so how you should read this logical circuit is that at each repetition, one of the angles is chosen and one of the 2 qubit operations is chosen from the dash boxes. And so then we're going to compare this to a physical teleportation. So looking at doing teleportation only with the sort of physical qubits. and then also the error that we would get from doing a pair of C0 operations. And so these are chosen just because they have the highest error rate compared to the other operations that we do. And so what we can see from the results from this is that the error rate that we get per logical clock, so per logical circuit and syndrome extraction, is below the physical error rate. And the scaling of this, I guess the trend of this, maintains the error rate below the physical level that we measure as well. And so this is an important result, and certainly for error correction, as we move towards doing repeated error correction, that we can show that the errors in our system don't blow up, they don't expand, they don't get exponentially bigger after you do a couple of repetitions of these circuits. I wanted to highlight a couple of other results. I think possibly I'm running out of time a little bit. But firstly was a result on benchmarking, again, logical circuits, so looking at the quantum Fourier transform. I won't go into too much detail on this, but that's also a recent result. And also looking at logical teleportation. And so the papers here are really showing that we're moving away from logical component operations through to really doing circuits and really doing operations that will be very useful in future calculations. And I wanted to sort of end with a few slides on scaling our system. So we recently relaunched the H2 system, increasing the number of qubit counts. But we're going to need many more numbers of qubits for the kind of operations that we want to perform. And certainly as we move towards logical qubits, we'll need many qubits to be able to encode our logical qubits. And so this is a sort of a bit of a summary of the roadmap that we have at Quantinuum, starting on the left with our linear traps, moving towards our H2 systems where we have this sort of linear trap with a 1D boundary condition. And then as we scale to larger systems, the concept is to move towards these grid architectures. These are very beneficial in a number of ways. It allows us to have more to get more qubits onto our traps. It also allows us to rearrange our qubits more efficiently because there's more options to be able to swap them. And then as we move to larger systems and being able to tile these and have modular systems is how we can see these systems growing to very, very large numbers. But these systems don't come without their challenges. And certainly as we scale them, we'll need to make sure that we have the necessary control to be able to manipulate our ions and perform our gating operations. And so the two particular areas are in terms of the ion transport and how we can actually manipulate the ions around, and also being able to address them. And so on the first point of being able to address our ions, on being able to, I guess, manipulate our ions and move our ions around, we demonstrated recently that we are able to drastically reduce the number of wires that we need to be able to perform our operations. And this is achieved through a method called C2LR, where the idea is that each gating zone, each sort of qubit zone now has a sort of switch that can determine whether a qubit or a qubit pair wants to take part in an operation or whether it wants to stay stationary. And what this allows for is a single wire to be able to manipulate whether a qubit is involved in an operation, and then we can globally address the entire trap with broadcast signals. And so this massively reduces the number of signals that we need to get onto our trap. And this sort of demonstration on the left really shows what would happen if we stepped through it. But what I'm going to do is just show you a little bit more of a cartoony kind of demonstration of what this looks like. And so we start in our initial configuration. We can either apply our signal or apply our switch or not. And so this will condition whether the qubits will either move to the left or move to the right. We could then globally shift all of our qubits to the left, apply an operation only on those qubits that happen to be sort of in the center, back where they started, and then we can shift everything back to the right and then do an inverse operation to recombine them. And so you can see the two paths through here where either we've applied our quantum operation, and so this may be a gate, this may be a transform, or we haven't. And so this is how we can sort of scale our system. And what this kind of looks like when we apply this to our grid architecture and we use this to do our sort of qubit rearrangement is shown in this video, where you can see the ions which are the ions are always moving, so they're always going back and forth, and so this is determining whether they will take part in the transport or not. And so what we've done here is rearrange the qubits entirely. So initially they started with the sort of 1 in the top left, and now 8 is in that top left. So we've rearranged them into a sort of completely new configuration here. And this also does scale to much larger systems. And so here we see a random arrangement of qubits, and the lines between them are the qubits that we want to perform gates on in the next round of the computation. And so by using this C2LR operation, we can rearrange our qubits, swapping them around these junctions, and eventually all of the qubits that we want to operate on end up next to each other. And so this is really showing that, with this sort of simple wiring architecture, we can still, scale this to very large systems and efficiently rearrange them. And I finally just wanted to mention about the addressing the ions and being able to, perform our operations. Right back at the start, I was mentioning how all of our operations are laser mediated. And so as we move to larger systems, we're working on being able to integrate the photonics into our devices, and so that we can still continue to address ions with very high fidelity, but also doing it in a scalable way. And so, looking at even sort of the passive components, how do we route light around, thinking about novel nanostructures and how we can, really focus light onto ions, and then things like active components, modulators, how do we, condition the light fields that we need for our operation. And so one final slide is to really highlight that Quantinuum is much larger than the hardware that I'd mentioned and have been talking about through this. While it does play a very key role in this in the company, we do span the fields of sort of cybersecurity, chemistry, quantum AI. We interface with third-party platforms through Ticket, and all of this, sits above our H-series quantum computers. And so, I'd encourage you to go and read all of the other things that do happen in the company as well, which is much broader than just the work that I've talked about today. And so that's all the slides I had. So thank you everyone for listening, and happy to take any questions.
Great. So yeah, many thanks, Henry, for the nice talk. So if there are any questions from the audience, you can write them in the chat, and then I'll be happy to relay them. But actually, maybe let me start with one, because you talked a lot, of course, about, what seems nice about your systems, right, is that you can put the qubits, in the buffer region, and you can put them close together and so on, play around with that. So what I didn't understand is whether in your current 1D-like architecture, how limited are you? Because presumably you can go beyond, for instance, one-dimensional interactions, right? You can do, because you said all-to-all, right? But where you sit between all-to-all and one dimension.
Sure. So even in our one-dimensional trap, we can still rearrange the qubits arbitrarily. So if we have qubits that need to operate, we can swap them around. We can swap the ordering of in that one-dimensional trap. So it really highlights in that particular case how the sort of power of this. But the one-dimensional trap is limiting in terms of being able to rearrange. So doing these swaps does take a reasonable amount of time. So as we move towards the sort of 2D architecture, we have far more, I guess, routes to be able to rearrange the ions, which allows us to do that far more efficiently. And so that's why, we're sort of, the 1D architecture is a very useful architecture, and we've been developing that for a number of years to demonstrate, lots of very nice results. But that's why we're sort of moving away from that more towards the grid architectures in the future, to allow us to scale out in a second dimension, which should allow us.
And do you know, more like looking forward, if you can eventually get all-to-all kind of couplings, then presumably this is good for error correction, right? Because I mean, there's this, for instance, there's these LDPC codes that kind of seems to be very efficient. I don't know if this is something you could be looking into with your systems.
Yeah, I mean, you're right. The all-to-all connectivity really helps, not just from the error correction side, but just from the algorithmic side of being able to do fewer operations compared to if you only had some fixed architecture. And so, yeah, it does apply to a lot of codes. Obviously, our system is not designed for a specific code or a specific algorithm. It's a general purpose quantum computer. But yeah, being able to do these operations, the all-to-all connectivity, and certainly the mid-circuit measurement and qubit reuse is also important for error correction when we have to have ancilla states to be able to do our syndrome extraction. That this will be a necessary part of the system as we grow.
Yeah, makes sense. Yeah. Oh, thanks a lot. Okay, are there any more questions in the chat? Okay, seems that that's not the case. Yeah, so in that case, I think maybe we can leave it there.
Yeah.
Okay.
Okay.
Yeah. Thanks everyone for coming.
Thank you very much, Henry.
Thank you very much for having me. It's a pleasure to talk.
Yeah, this was very clear. Thank you.
Thank you. Bye.